Okay, so the last little part of this chapter is going to deal with how we define the composition of solutions. Okay, and so this kind of, I don't know, for me, this doesn't really fit here. It fits somewhere else. But I'm going to quickly define what a solution is, and then we're going to define how we actually quantify or how we specify the composition of various solutions. Okay, okay, so number one, what is a solution? So a solution, if we go back to chapter 1, I think, is a homogeneous mixture of two or more substances. Okay, and so if you guys remember what a homogeneous mixture is, that just means that when you put these two or more things together and you mix them, they're going to be uniform throughout, right? So a good example of that would be like, I don't know, iced tea or something, just tea, period, coffee, right? Those are two or more things going in to make that, but there's no difference between if you pull from the top or if you pull from the bottom. You're going to get the same exact uniform distribution of things throughout, okay? So that's what a solution is. Now, there are going to be two important components to a solution, okay? So the first one is what we call the solvent, and the second one is what we call the solute. I kind of did that backwards, but it's fine. Those are the two. So we have solvent versus solute, okay? So together, these guys make up the solution, right? So a solution is the combination of the solvent and the solute. Now, how does solvent and solute differ from one another? So the solvent tends to be what we consider the major component of the solution, whereas the solute tends to be the minor component. And another way we could look at this is the solvent tends to maintain its phase when we actually make the solution, whereas the solute tends to change phase when we make the solution. And what I mean by phase, I mean physical state, right? So a good example of this is, let's say, making a salt water, so NaCl solution. And this is going to be kind of like defined generally as what we would call an aqueous solution, because for the most part, pretty much all the solutions we're going to be dealing with are aqueous. And in an aqueous solution, the solvent is water, right? So usually in all of the chemistry we're going to be doing, in general chemistry at least, our solvent is going to be 100% of the time water for the most part. And again, that is just defined as the solution is aqueous, right? The water is a solvent. That's what aqueous stands for. Okay, so let's say we're making an NaCl solution, so a saltwater solution. Again, this is going to be an aqueous solution, right? So we have our beaker here, and we've got water in it, right? And so we put in sodium chloride, right? When we put sodium chloride in, we don't put it in as like a liquid, right? We usually would just take table salt. This is a solid. We put it in, it goes into solution, and when we stir really hard, it essentially appears to disappear, right? This is what I mean by changing phase. It was a solid. When we put it in to make the solution, it changes phases. Now it actually becomes what we call aqueous. It's now dissolved in water. The water itself doesn't change phase. It was liquid before, it stays the exact same liquid form after, okay? So two different ways you can look at solvent and solute, major component versus minor component, or the thing that maintains phase versus the thing that changes phase, okay? Okay, so that's like a basic overview of a solution. We'll talk in a later chapter about, let's say, what happens to these NaCl particles as they go in here and what actually occurs when they dissolve. I'm not going to talk about that right now. But just as a note, because solutions are mixtures, we actually have to specify how much of the solute we have relative to the solvent, right? Because that can differ. We can change that. So for example, let's say in our first saltwater solution we made, we put in 10 grams of NaCl, right? Let's say that we had a liter of water, and that's what we did. We stirred, it dissolved, we made our solution, right? Now, that is going to be different from another solution where, again, we have, let's say, 1 liter of water, and let's say we put in 50 grams of NaCl, right? So we put it in, it's solid, it dissolves, we made a solution, right? we could say that both of these are NaCl solutions, right? Both of these are saltwater solutions, but they're different, right? This guy's got 50, and if you tasted it, it would taste really, really salty. This guy's got 10, it's got less, right? It's not going to taste as salty. They are different solutions. And so because of that, we have to specify anytime we're dealing with these types of things, the actual amount of solute there is relative to solvent, because that's going to change the overall solution. Okay, so that's kind of like the basis, the background behind what we're going to talk about. Now we're going to talk about how we actually specify that, right? How do we specify how much solute there is relative to solvent in chemistry? Okay, so the first way that we do is what we would call a qualitative essentially definition, right? And what I mean by qualitative is it's kind of like hand wavy, right? It's not specifically defined, but it does give you an overall idea in relative terms, what's going on, right? And so if we go back to that 50 NaCls versus 10 grams of NaCl, and we wanted to describe these guys in a qualitative manner, the one that has less, the 10 grams, we would call that dilute, right? So this guy would be our 10 grams of NaCl. And the one that has more, that's got a lot of stuff in it, that's what we would call concentrated, right? So a concentrated solution is one that has a lot of solute versus solvent, whereas a dilute solution doesn't have a lot of solute versus solvent. Again, this is hand wavy, right? We're not telling you specifically how much there is. We're just kind of giving you an idea overall. Oh, this is a very concentrated solution. We know that it has a lot of solute versus solvent. This is a very dilute solution. We know that it has not that much solute versus solvent. Okay, so then how do we actually quantify how much there is of solute versus solvent? So the major unit that chemistry utilizes to specify the concentration, and that's what we mean by this amount of solute versus solvent, we define that as the concentration of a solution, is something called molarity, right? So molarity has a very specific definition. It is defined as the amount of solute in moles. So this is going to be moles of solute. And again, the solute is the minor component. In our example, this would be the NaCl. And this is going to be divided by volume of solution. And this is in liters specifically. So this is liters of solution. So just as a note, right now, note that, okay, this is moles of solute, but down here, this is solution, right? And so remember that solution was not just the solvent, it was the solute plus the solvent. And that's going to be, I'll kind of specify what I mean by that in a second. Okay, so this is it. It's going to be how we quantitatively define the amount of solute relative to solvent in our chemical expressions and our chemical calculations, etc. We're going to use molarity. So just as a note too, molarity does have its own unit. It's capital M. You can also specify this as moles per liter. You can use those as units, but you do need to specify either capital M or moles per liter. Okay, so let's say that we were making a solution, right? And so a lot of times in the lab, when you actually perform a lab, when we make solutions, we use a very specialized piece of equipment called a volumetric flask. So this is what a volumetric flask is right here. So this is volumetric. I don't know if that's how you spell it, but it's good enough. And so what volumetric flasks are, oh, here it is, yes, is they're very, very, very accurate for one specific volume, right? So, for example, in this volumetric flask, this measures 1 liter of water very, very, very accurately, right? But it doesn't measure anything else besides that, just 1 liter total volume of solution, okay? And usually where that measuring is on the neck of the flask. There's usually a line, right? And so whenever the meniscus of the water hits that line, that means that there is total 1 liter of solution totally. Yeah, okay. Okay, so let's say that I wanted to make, let's say a 1 molar NaCl solution, right? And so if it's 1 molar, so 1 molar, that means that there is 1 mole of NaCl for 1 liter of solution. Right, so now if we think about this in terms of like stuff that you can actually do in the lab, In the lab, we have balances that measure masses, but we don't have balances or anything that measure moles. So the question is, well, what is a mole of NaCl? How would I be able to measure that, right? And so this goes back to the entire definition of molar mass, which we talked about already. And so if I need a mole of NaCl in the molar mass, so this is 1 mole of NaCl, and the molar mass of NaCl is 58.55 grams per mole. For every 1 mole of NaCl, there are 58.44 grams. So I would need to measure out 58? Yes, 58.44 grams of NaCl, right? So that's number 1. This is per liter of solution, right? So if I had a liter volumetric flask, the first thing that I would do is I would dump in my mole of NaCl, or what I've measured out, 58.44 grams of NaCl. I would dump it as a solid, right? Then what I would do is I would fill the flask, the volumetric flask, about half full of water, and I would completely dissolve all of the solid. And there's kind of an important point to this, and that's the only reason why I go over this. So I would stir, shake until all of the solid dissolved. Then I would fill the rest of the flask up with water until, again, the meniscus hits that nice little line on the neck of the flask, okay? That is how you would make a 1 molar NaCl solution, specifically 1 liter of it. Okay, so you may say, well, why would you do this step? Why wouldn't you just put the solid in and then fill up with water all the way to the neck of the flask without, worrying about dissolving? And the answer to that is the actual solid takes up volume, right? So if I were to do that, if I were to put the solid in, and then I would fill it up all the way to the neck of the flask, and then I would dissolve, essentially what would happen is the level of the water would rise past that line. And so we wouldn't have an actual 1 molar solution because we wouldn't have a 1 liter total volume solution. We'd have more at that point in time. So just note, it's 1 liter solution. It's not 1 liter of solvent, which is what I would have been doing if I had just filled it up 1 liter of solvent before dissolving everything. Okay, so let's go ahead and go over an example where we do some calculations with this. And then there's probably a problem that I let you do next, okay? So let's say that we have, in this example, 45.5 grams of magnesium chloride, and we are dissolving it in enough water to make 2.75 liters of solution. They want to know what the molarity of the solution is. And they spell solution correctly with the N. Okay, so first thing we need to note is, first off, what is the definition of molarity? So molarity is defined as the number of moles of solute divided by the total volume of solution in liters. So this is liters of solution. All right, so right now what we do know, we already know the liters of solution, right? It's 2.75 liters total, and they give us that. What we need to know to go ahead and calculate molarity is the number of moles of solute. And unfortunately, they don't give us moles of solute, they give us grams of solute. And again, the solute here is magnesium chloride, water is the solvent. So how do we go from 45.5 grams of magnesium chloride to moles of magnesium chloride, right? So this is where the molar mass comes in handy, the molecular weight of the molecule. So for magnesium chloride, the molecular mass and molecular weight, whatever you want to call it, is 95.21 grams per mole, right? So if we had 95 grams, we'd have a mole. We don't have 95 grams, right? We have a fraction of that. So the question is, well, what fraction of a mole do we have, right? So we're going to convert from grams to moles by taking the molar mass and dividing, right? So for every 95.21 grams, there is 1 mole of magnesium chloride. So grams canceled, we're left in moles, and we'll figure out what that number is. 45.5 divided by 95.21 gives us 0.478 moles of magnesium chloride. So that's it, right? Now we know the number of moles of solute. We'll go ahead and put that in. So 0.478 moles. And then we'll divide by the total volume of solution. And that ends up giving us a molarity of 0.174 molar. And again, I use this as a capital M. That's usually how I, with respect to units, that's usually how I define molarity, with a capital M. Okay, so, they've given us the amount of solute. It's in grams. We have to convert. They've given us a total volume of solution. We should be able to calculate the molarity of that solution. Okay, so now this is kind of a little bit reversed, right? In this one, which you're going to do on your own, they give you the molarity. So they define that. And again, 1.5 molar, that's what the capital M is. They've given you the volume, and they actually want to know what mass of our solute, which ends up being potassium chloride, we need to actually make this solution. So go ahead, give this one a shot, pause the video, and then come back for the answer. Okay, so again, they've given us molarity for this one, so I'm going to go ahead and write out molarity is equal to moles of solute divided by liters of solution. And I'm going to try to define everything that I know about this problem already, okay? Number one, we know the molarity, so I'm going to go ahead and plug that in. So this is 1.50 molar is equal to, we don't know moles of solute, right? We are being asked specifically what the mass of the solute is, so we know that that's probably going to be an unknown, but we do know the volume of solution, right? The only problem with this one is that this is in milliliters, and for our molarity calculations, we need to convert to liters, right? So the first thing that we have to do is convert this to liters, and we can do that. So 25.0 mils, there are 1,000 milliliters in 1 liter. By dividing by 1,000, that's just going to move the decimal place 3 places to the left. So we have 0.250 liters. So now we can go ahead and plug that in. We have 0.250 liters. And this is going to be like our unknown. We're going to treat this as an algebraic type problem here. So we have one unknown, we have one equation, we should be able to solve for that. To solve or to isolate x, what we're going to do is multiply both sides by the denominator here, this 0.250. So I multiply this by, multiply this by 0.250, multiply by 0.250 to both sides. These guys will cancel. We'll be left in x on the right, and then 1.5 times 0.25 gives us 0.375 moles. So if I want to solve for the number of moles, and I know the molarity and the volume of solution, I just need to multiply the two to solve for the number of moles, specifically KCl. Now, again, this is great. This is part of what we wanted, but they actually want us to know what the mass of it is, because again, in the lab, if you're going to make the solution, there was no mole machine, there was only a balance, right? And balances measure masses. So we need to take these moles and we need to convert to the mass, and we'll do that utilizing the molar mass of KCl. So we have 0.375 moles of KCl. This is a little bit different than before. When we had it grams, we needed to convert to moles. We divided by the molar mass. When we have a moles and we need to convert to grams, we're going to multiply by the molar mass, right? So for every 1 mole, moles go on bottom, 74.55 grams of KCl, right? So we multiply and divide. Moles cancel. We're left in grams of KCl. And specifically, this is times 74.55 gives us 27. Oh, well, that would round up. And I kind of made a little error when I did this multiplication. So if you get a little bit different, don't be worried. So this ends up being 27.98. So I'm going to go ahead and round up 28.0 grams of KCl. And so if we wanted to make the solution, we do all these calculations, then we go measure out 28 grams of KCl. We put in our little 250 ml volumetric flask. We'd add water to like halfway. We'd shake to dissolve everything, and then we'd fill it up to the line on the neck of the flask. Okay, so one other little aspect with respect to solutions and concentrations is something called dilution or solution dilution. So frequently, when we're in the lab, we'd like to make what is called a stock solution. So something like it's very, very, very concentrated. Let's say it has like a molarity of 10 molar. And let's say this is like a very common solution that we frequently utilize. So let's say this is like salt, again, so a saltwater solution. And then from that concentrated stock solution, we'll just make dilutions, right? So it's a little bit easier to make that concentrated stock and then dilute it to make whatever solution you want, as opposed to just making the solutions individually every single time, okay? Okay, so again, our stock solution is what we would call a concentrated solution. And if we needed to dilute it, right, if we need to make it less concentrated, what should we do? Right, so for example, if your iced coffee or your iced tea is too strong or it's too concentrated, what do you do to make it like better or easier to digest, right? Either you add either you add milk or you add water, but essentially you're going to add something to it to dilute it. And with respect to our aqueous solutions, what we're going to be adding to dilute it is going to be water, right? So how do we dilute these concentrated solutions? Where we increase their volume, we add water to them, okay? Now, there's a little equation that makes these calculations really easy, and it's called the dilution equation, right? So I frequently refer to this as the dilution equation. There's a couple different ways that you can see it, depending on what class you're in. So we use this M1V1 is equal to M2V2, where the M's stand for molarities. So molarity 1 or molarity 2, these guys are molarities. And then V's are volumes. This is also can be defined as molarity concentrated, volume concentration is equal to molarity dilute, volume dilute. Or some other ways that you'll see it is C1V1 is equal to C2V2. The C's and the VMs, they just kind of replace one another. Because again, we're dealing with molarity frequently in chemistry. Okay, so how would we actually go about doing one of these dilution problems or doing one of these dilution situations? So let's say that we had a concentrated stock solution of calcium chloride, and we had that sitting around in the lab. And the concentration of that was 10 molar. Let's say from that, we wanted to take a volume of that and dilute it to make 3 liters of a 0.5 molar calcium chloride solution, okay? So how would we do that? How would we go about making this solution? So number one, we would bring out our handy dilution equation. So we have M1V1 is equal to M2V2. And then we would identify all of the things that we already know, right? So number one, this M1 is always going to be the concentration of the concentrated solution of the stock solution. So that ends up being this guy, right? The highest concentration, which is 10 molar. So this is what we would call M1. The question here is how much do we need to take of that, right? If we're going to take that and we're going to dilute it, what volume do we need to actually dilute or take from it? And that's what's going to be defined as V1. And right now, we don't know what that is, right? That's the question that we're actually going to be answering. Now, we do know the other side, the diluted part, right? This is going to be our diluted stuff. And we know that the concentration of our diluted solution is going to be 0.5. So this is going to be M2, and we know we want to make a total volume, or a V2 total volume of 3 liters. So 3 liters ends up being V2. Okay, so now, again, we have an equation, M1V1 is equal to M2V2. We have 3 knowns, we have 1 unknown. We're going to plug everything in, and we're going to solve for our unknown, which is volume of that concentrated solution. So we've got 10 times, we'll substitute x in for the little question mark, is equal to 0.5 times 3. So if we go ahead, multiply, and then divide both sides by 10, so we got 0.5 times 3 divided by 10 gives us 0.150, and we're in units here of liters, because when we divided both sides by that 10 molar, the molarities canceled. And again, we're looking for a volume anyways, so our units are good. Okay, so now what does this mean? Again, 0.15 liters, if we convert it to milliliters, is 150 milliliters. And so what we would do is we would go to this stock solution. We would measure out 150 milliliters of that stock solution. And again, we would put it into our volumetric flask, just like we did with the solid NaCl, okay? Now, this is 150 mils of that concentrated stock solution. Now we need to bring that total volume up to that V2, to that 3 liters, and the concentration of the solution that results is what M2 is this 0.5 molar, okay? So we add our 150 mils, then we add water until, again, the meniscus hits the etched line on the neck of the flask. So this is 3 liters total. This is our V2. And again, its concentration is M2. It's our 0.5 molar solution. Okay, so again, 10 molar stock was M1. And we solved for what volume do we need of it to make this new solution, our new dilute solution overall. Okay, so go ahead and try this one on your own. Similar type problem. We have a concentrated stock solution, so it's 6 molar sodium nitrate. They want to know what volume do you need of that solution to make a dilute solution that has a 1.2 molar concentration and specifically 0.525 liters of it. So go ahead, pause the video, try this one on your own, and then come back for the answer. Okay, so this is very similar to what we just did. We've got our M1 V1 is equal to M2 V2. Again, this side of the equation is the concentrated side. This side of the equation is the dilute side. Our concentrated molarity, our M1, is this 6 molar. Our concentration of the dilute side is 1.2, so this is M2. And then our volume of the dilute side is this guy, 0.525. So again, we're going to be solving, for V1. What volume of that 6 molar solution do we need to make 1.2 molar solution, 0.525 liters of it? So we'll go ahead and plug everything in. We've got 6. Again, the V1 is this unknown. We'll leave it as X. Then we've got M1, which is 1.20 molar. And then we've got 0.525 liters. So I'll multiply the stuff on the right, 0.12 times 0.525. This gives us 0.63 is equal to 6x. So then we'll divide both sides by 6, divide both sides by 6. We're left with x equal to, divided by 6, 0.105 liters. And again, we're in liters because this guy was in liters, and these were both in molarities. Now, as a note, again, I always try to take things back to the lab because, there are important units that we will frequently utilize in measuring stuff that aren't necessarily specified when we're just going through the textbook. But frequently for volumes, we measure milliliters, right? A lot of the graduated cylinders we use, or a lot of the volumetric flasks are in milliliters. So easy conversion that you should kind of put at the forefront of your mind is this liters to milliliters conversion. So if we have 1.105 liters, to convert that to mils, we're just going to multiply by 1,000 or move the decimal 3 places to the right. Right, so this ends up being 105 milliliters. And again, just getting in the habit of that because the milliliters is usually what we measure. The liters is not so much what we measure. Okay, so that's it for this. Your textbook goes over a couple other solution concentrations and ways that we can define it. Again, I would go over that yourself. A lot of the concepts are exactly the same as molarity. It's just they just defining something differently. But yeah, that's all I have for solution concentration.